You're probably looking at that and thinking, wow, that is the jankiest shaper tool holding setup ever. Excuse me, I'll have you know it was nominated for but did not win at the 2025 Jankies. Therefore, it is no better than second jankiest in the world. I mean, it did win a 2024 Golden Jank Award, but nobody cares about those. Hello, Internet. My name is Quinn, and this is Blondihacks. I've got a tool build for you this week. I'm soon going to be in need of some sort of rotational indexing or dividing fixture for my shaper. I've got a bunch of projects lined up where that would really be helpful, so I'm going to see if I can come up with something right now. I started by trying to find some existing fixture that I might have that could be used for rotary indexing on the shaper. I do, of course, have my 6-inch Vertex rotary table, but as you can see, it is comically oversized for this machine. To understand my design decisions here, you have to understand how small this shaper actually is. My 4-inch rotary table is a pretty decent fit. However, by the time you get a chuck and everything on there, the entire work envelope is actually consumed by this setup. So again, not even close to working. Atlas actually did have their own design for this type of thing. It used 2 centers on a common frame, and it had little indexing plates and a little drive dog clamp thingamajig. It's actually quite a nice design. I did look into acquiring one of these. Unfortunately, not very many were sold, so they are pretty unobtainium nowadays. I also considered copying this design. This design has a lot going for it. Obviously, centers give you guaranteed concentricity on your work. The usual downside to working between centers on something like a mill or a shaper is that you have a separate footstock with one center and your work holding on the other, and you have to get those 2 centers perfectly aligned on the table before you start. You've seen me do this in some setups on my mill for rotary operation, and this is a lot of work. It can take an hour or more to get those 2 centers properly aligned. There's a lot of variables in all 3 dimensions, and every adjustment affects every other adjustment, and it's a long process. Now, what's clever about the Atlas design is that they've put both centers in the same fixed casting, so you don't have to align them. You just put that whole casting right on the table, and you're ready to go. And I really like that. Unfortunately, the challenge for me with this would be manufacture. Those 2 centers in that common casting are quite far apart and not very large in diameter. So really what you'd want to do is line bore that to guarantee alignment of the bores, but because of the small diameter, it's not big enough to do a line boring operation. I don't know how they made these in the factory. My guess is they probably had some sort of specialized machine that bored both ends of it at the same time. I can think of a few possible ways one might make this in a home shop, but honestly, it's not really necessary. I think I can sidestep this whole thing because I don't need to work between 2 distant centers like this. All of the parts I want to make with this are disc-shaped. I'm talking about gears and ratchet wheels and knurled knobs and that type of thing, so I don't need to work between centers. I just need some sort of shallow work holding system at one end. The next question is how to do the actual indexing. My Vertex rotary table comes with indexing plates and the sector arms and the little crank handle and so on, all the pieces necessary to index with the rotary table, so this was appealing if I could somehow reuse these parts. The other thing I did consider was using the change gears on my lathe as indexing plates. This is something model engineers have been doing for 100 years. Your lathe came with a whole bunch of gears, so you have a whole bunch of tooth counts and all of the factors and multiples of those tooth counts that can be used for indexing. So a lot of times model engineers will set up an indexing fixture on the back of the spindle of their lathe, something like that, to index with these gears. Now, the nice thing about indexing plates is they're all the same size. If you use change gears for indexing, well, they vary dramatically in size depending on tooth count, so your indexing fixture has to somehow accommodate that, which adds a lot of complexity. The next challenge is whatever I build has to be very compact. It may not be easy to appreciate on video how small this shaper actually is. The work envelope is about the size of 2 fists, so whatever I build has to fit in that. I also brought out a couple of samples of the range of mandrels that I would want to work with for work holding. So that gives me a sense of how big some of the components need to be. I set the center of the fixture at 2 inches, which is half the Z capacity of the machine, which should give me the most possible working range for different diameters of parts. And extremely luckily, that is just enough to get these Vertex indexing plates off of the table, so they can fit on a 2-inch center without touching the table, just barely. I went through a lot of designs for this. And I mean a lot, but this is the one that I landed on. I felt like it solved all of the aforementioned problems with the fewest number of components and each component being as simple as possible, and also fit within the materials I had on hand. All of those constraints together landed me on this design. So in yellow is the big indexing disc, in green is a bushing that goes all the way through the pink frame, and then in yellow is the main axle, which acts as workholding on the right side with 4 little set screws, and on the left side is a copy of the end of that shaft for the vertex rotary table so that the accessories for the indexing will all fit onto that. Workholding was a big challenge to solve as well. I opted to go with a standard collar with 4 set screws to hold it. And the idea is you'll turn that standard mandrel size onto every workpiece, which is not a big deal. Coming up with some sort of flexible workholding system without reinventing the chuck and also doing it in a very small space is actually really difficult. So this is what I landed on. As I'm sure some of you are thinking, why not use an ER collet closer as the workholding? And I did consider that, but even a very small one, such as this ER20, is a lot bigger than you think it is, and this shaper is, again, a lot smaller than you think it is. By the time you get an ER collet closer on the front of the frame and modify it to have the indexing plates and so on the back, well, you've got a lot of stick out, you've lost a lot of work envelope, the rigidity is going to be poor, and, well, it's just a lot of complexity to the design that I don't think is necessary. If my little collar idea doesn't work, then plan B will be to try a really small collet closer, like a watchmaker's maybe, like an ER8 or an ER16 maybe. Those would be small enough, but I'm going to try this collar thing because it's easy to do and nice and simple is always best if we can do it. I gathered up all the materials to begin with. As I said, I tweaked the design until it fit within all materials that I had on hand. I really didn't want to order anything for this job. I'm going to start with the main frame, which is all solid steel, and because of the complex shape of it, I decided to do this as a weldment. If this was a factory piece, of course, they would make patterns and cast them, but if you only need one and you don't happen to have a cast iron foundry in your workshop, then a weldment is the next best thing. What you do is you make all of the components rough and oversized, weld them all together, let all of the warping happen just like in a casting, and then machine everything to precision after the fact, just like you would with a casting. I'm going to machine a couple of dimensions first, though, that aren't going to matter if they move a little bit, and that's the ends of the main frame and the ends of the feet. This is going to ensure I can get square welds and so on. Speaking of welds, I'm going to do a very generous weld prep on the feet, make sure I've got plenty of weld penetration. I'm going to bevel all 4 corners that are all going to get welded all the way around. Next, I want to cut the corners off of that square block to create the overall shape of the part that you see in the corner. I kind of need to do this now because once the piece is welded into the complex shape, it's going to be really difficult to put it into any kind of machine. And I really only have one machine that is practical for making these heavy cuts in this steel, and that's my horizontal bandsaw. So I've roughly laid out where those edges need to be based on the bolt circle at the top and the feet and so on, and that's going to give me enough information to do some rough bandsaw cuts that are oversized, which I can later machine down. But if I don't make these cuts now, I'm never going to be able to do them, and there's just no other practical way in my shop to remove that much steel. Machining all that away would take hours and probably consume multiple cutters, but by bandsaw cutting them off, I've got these little wedges that'll go in the scrap bin, and I'll use them for something someday. Now I'm ready to weld the feet on. Again, this is all still at the low precision stage, so if everything warps and shifts from the welding, it doesn't matter. But I'll tack those in place. And then once they're tacked all the way around, then I will weld everything up fully. I'm using flux core MIG for this, which is not the correct welding process for a job like this, but it's the welding process I have, so it's the one I'm using. The welds are going to be ugly, and yes, I should have used TIG. If I had that set up and the skills to do that, I would have. I know all the things, but this is going to work, so stick with me and the welds will get cleaned up. It's all going to be okay. I promise. Flux core MIG doesn't get a lot of respect in the YouTube welding world, it seems. All the cool kids TIG everything, but honestly, if like me, you weld one thing a year, flux core MIG is awesome because it can do most jobs adequately, and you don't need the big gas tanks and dealing with all of that, and your whole welding setup takes up 1 cubic foot in the corner of your shop, and it's there when you need it. Once that's cooled down, I can set it up in the mill to machine the bottom flat. That's going to be my first reference surface. Again, I'm machining this just like I would a casting. I'll start by tapping in the top edge of that bar as flat as I can get it. Now this is not a machined surface, so you may not be able to get this perfect, but the goal is minimal material removal. So I get it as flat as I can, and then take light cuts from here to machine it flat and take off as little material as I can that'll clean up those welds and clean up all of the cold rolled surface. This seemed to be going well, but somewhere around here is when I realized I had missed something. More on that in a second. You can see that was going well before I aborted. A little bit of porosity in one weld and a little bit of undercut in some of the others. I'm not a very good welder, but it was going fine. A little bit of a low spot on this foot still because I aborted, as I said. The reason is I forgot to weld the gussets on top. So, yeah, you have to do all of the welding before you start machining or else everything's going to move again. Luckily, though, I took some measurements and I actually still have 20 thousandths to remove. So if I'm careful, I can go back and weld these little gussets that I just made in place and remachine everything, and I may just get away with it. That's not going to stay there on its own, so I'm going to have to weld it in, which means I got to machine these welds out of here so that the gussets can sit flat. This end mill that I'm using is a bit of an unusual beast. It has chamfered corners on it, so it's actually creating chamfers on the insides of those. It's got a pretty high tool pressure because of that, but in just a couple of passes, it's removing the weld and leaving me a nice little chamfer in there for strength. I also knocked the corners off my gussets so that I can sit them in there and weld them in place. To try and weld these in with minimal heat so that nothing moves very much, I'm doing the old stack attack. Rather than welding a bead in there, I'm just stacking tacks one after the other. Again, sorry, I'm not a good welder. It's not very pretty, but let's see how I actually did on the heat management, which is all that matters. So once again, I got it level using that machined surface. The main frame didn't shift. I didn't expect it to. It's a 40-pound block of steel. The feet, however, did pull down about 5 thousandths, which is what you'd expect. But as I said, that's great news because I have 20 thousandths to remove still, so I'll have no trouble getting this flat after that second round of welding. And I landed right on the correct overall dimension, and I'm pleased to say a quick check on the surface plate shows this thing is dead nuts flat. At least as flat as I can make things in my shop without a surface grinder. Very pleased with that. I almost didn't bother with those gussets after I realized my mistake, but I thought, they're probably important for rigidity, and well, yeah, I think it was worth going back and fixing that mistake because the whole system will be a lot more rigid with those in there. The next thing I did was the countersunk bolt holes. These are going to be useful for fixturing, so I want to do these now. Oh, she's checking tram. That can only mean one thing. The fly cutter is coming out. I don't check the tram on my mill all that often, honestly, because here's a dirty little secret that enthusiastic new machinists seem often unaware of. Tram is not nearly as important as you think it is. In a hobby environment where you're mostly using small diameter cutters, tram has very little effect on anything. The overall flatness of a surface is the average of the high spots of that surface, and as long as the diameter of your cutter is smaller than the surfaces you're cutting and is small itself, say half an inch or less as is typical in a hobby shop, then tram is having very little effect on your work. However, once you get out something like a fly cutter or a large diameter face mill, then tram matters a lot because you don't want to start creating water slides on the top of your part. Next, I'm going to bring in an angle plate. This is going to hold my work because I'm going to do all of the critical relational surfaces on this frame all in one setup. I, of course, align it along the x-axis of the machine, and I also check it for verticality because my experience with this cheapo angle plate is that it's not really usually 90 degrees, and I often have to shim it to get it to zero out vertically. Now, I guess 89.5 degrees is an angle, so it's not false advertising that they call it an angle plate. Amazingly though, this time it measured square, so I'm not going to look a gift 90 in the mouth. I'll bolt the frame on there now, and once again, dial this in as flat as the factory cold rolled surface will let me so that I can get minimal material removal and end up with a flat surface. The goal is to create a surface that's as perfectly square to that machined bottom as I can get, and that's why I'm doing it in this angle plate setup. For support, I'm adding a machinist jack. I've got the indicator on there to make sure I don't jack this thing up out of flat. That's easy to do with those jacks. Then I clamp the other feet in place for a little extra support, and in comes the fly cutter. I'm taking a very, very light cut here. The goal is not to hit any kind of dimension. The goal is just to clean up that factory cold rolled surface and get something as flat and smooth as I can. So the best way to do that with a fly cutter is very, very light cuts. I think this is a 2 thou pass that I'm doing, just enough to clean it up, and a very low feed rate. That went well. I'm reasonably happy with that. This is 1018 steel, which doesn't fly cut all that well, but it's okay. Now, while in this same setup, without touching anything, I'm going to do the main bore that holds the axle. And it's really important to do this in the same setup because then it's going to be guaranteed parallel to the bottom of the frame and square to the top surface, or what's going to be the front surface of the frame. Any error in all these relationships is going to be telegraphed into every part I make with this thing, so it's important to get this right. I pre-drilled that, and then I'm going to come in with the boring head to make sure I get a very round hole that's right on dimension. Regular viewers will know the boring head is probably my least favorite milling job, but I will say that this little hand wheel I added to the quill recently really, really helps. It makes it much more pleasant to do these long, slow boring head cuts through thick material like this, especially when you're doing a lot of passes. And then you can quickly retract it with the little handle. This has reduced the annoyance of boring heads on a machine like this by probably 50%. I hit my dimension on that bore, but something didn't seem right. I had a little moment here where I'm like, wait, how can it be that the axle is 12 millimeters, it goes through this, and then the bushing goes around the axle and also goes through this 12 millimeter? Oh no. Yeah, so the thing about CAD is that it's very easy to accidentally design things that intersect without you realizing it. And that is what happened here. I caught a stroke of luck here, though. I went back to the model and increased this bore to the OD of the bushing and not the axle, and there's just enough room in the frame for me to get away with this. The web at the top of the frame is going to get a little thinner than I'd like, but that material up there isn't really doing anything anyway. It's got plenty of support all the way around, so that bore I just did became the world's fanciest pilot hole for a great big drill, and now I can come in once again with the boring head and bring this out to the actual correct final dimension. The axle is 12 millimeters in diameter, and then the outer bushing that holds it is 21 millimeters. These are all metric, of course, because again, I'm matching the parts on the Vertex rotary table, which of course is built-in metric. For that same reason, next comes a 32 millimeter bolt circle to match the bolt circle that's in the indexing plates. Those plates will bolt directly to the frame, so they'll be nice and square to the work because again, they're clamping against this frame surface that I know is square to the base. I'll do a quick check, make sure that these actually fit on there and that the center bores align and so on. And that's all looking really good. You can see as calculated, the plate just clears the bottom of that frame. That is very lucky. Well, I mean, I did plan it, but still, it was lucky that it worked out this way for my shaper. Now, I don't have a really good way to check squareness. I don't have a fancy squareness comparator or anything like that. I do have a square standard that I can put up against it on my surface plate and shine a light through there. And according to this method anyway, it's as square as I think something can be. There's no light coming through there other than a few specks where the surface finish from the fly cutter isn't perfect. I did the same check with my Starrett square, which I trust, and same story, no light coming through except imperfections in the surface finish. So very happy with that. I'm going to pause here and go on to the next part, even though there's a lot of finishing work left to do on the frame, because I want to know this whole thing is actually going to work before I put in the effort to make it all look nice. The next piece then that I'm going to make is the main bushing that goes through this bore, and I've got this really nice piece of bronze for the job. Just need to make that go in there. It doesn't fit. Well, I've heard so much about this whole machining thing, I guess I'll give that a try. I have this lathe machine on my bench, and I read the instructions for that. I think I got the gist of it. I'm going to face off the front of that, as is tradition. And then I'm going to pull that out and put a center in it, because all of the features on this part need to be made in a single setup. That's really important so that everything's concentric with everything else. You can get extremely accurate and concentric parts on a cheap 3-jaw chuck like this, as long as you meet a series of conditions. You have to do absolutely everything in a single setup. You cannot touch that chuck at all once the material is in it. And you have to cut every single surface on that part in this setup. And the shallowest cut on your part has to be greater than the runout in your cheap chuck. If you do all of those things, This part will be as accurate as the spindle bearings in your lathe, which even on pretty budget-friendly lathes is going to be excellent. Because of that, model engineers will jump through a lot of hoops to make a part in a single setup to squeeze the accuracy out of their inexpensive lathes. After the largest OD is turned, I'm going to create the flange at the far end of the part, and I'm going to establish this shoulder with a grooving tool. This has to be done flange outward because we're going to have to be boring, which again means we have to do it facing outward so we can do it all in one setup. This would be a good opportunity to use a left-hand turning tool to turn up to that shoulder, but I couldn't find my left-hand turning tool for brass and bronze, so I instead established that shoulder with the grooving tool, and then I'll use my right-hand tool. Then while that cut was running, I looked at the back of my tool holder and realized my left-hand turning tool is on the other end of this same tool bit. So I stopped, flipped it around, and switched to left-hand turning, which is a much better way to get this diameter and get the back of that shoulder accurate at the same time. Here's a dirty little secret for you. I actually missed the dimension on the boring head operation a little bit, so I left the bushing a bit oversized, so I still have a good fit there. And then the far end where the vertex indexing stuff's gonna attach, I turned that down to the correct 21 millimeters that it's expecting. That's why you always do internal diameters first, because it's very easy to match outer diameters to internal ones if you blow the dimension. Survey says, close enough. Now I come back in and do an undercut under that shoulder, and this is important because I want to guarantee that shoulder is sitting firmly against the frame. This flange at the end of the bushing is a thrust surface that's going to transfer the substantial forces of the shaper through the part and into the frame so that this bushing and the axle aren't trying to take those forces. And there's a little groove at the end that takes a little spring clip that's part of the vertex indexing system. Then, of course, chamfers are what separate us from the animals, so let's go break all those edges. Now it's time to do the internal features, but again, got to do all this in one setup. So out comes the tailstock, and in comes the steady rest, and I'll very carefully touch these rollers into place without moving or deflecting the part at all. And this will allow me to do all the internal features and maintain concentricity, even with a cheapo chuck. The stick out on this part is not terrible. It was sort of borderline. I might have gotten away with not using the steady in this case. I am going to be doing pretty light cuts, not a lot of lateral forces, but figured better safe than sorry. So I went up a couple of drill sizes, working up towards that 12 millimeter diameter for the main axle. Now I'm going to want to bore this for concentricity, but I can't bore something that deep. My smallest boring bar that will fit in that hole doesn't have the reach needed. But I do have a 12 millimeter reamer. So I'm going to use a little trick that's worked for me well in the past. I'm going to bore as deep as I can with a small boring bar to create a concentric bore that's a little bit smaller than 12 millimeters. That's going to act as a pilot bore for the reamer. Reamers, of course, can't create concentricity, but if you start them in a very concentric hole, they will stay in that track. They will create concentricity from there down. So the bottom end of this hole is still the pilot drill size, the rough drill size, which is not round or concentric, but the outer part is a concentric bore, slightly smaller than the reamer. So the reamer cuts this outer part to dimension. Then when it gets into the drilled portion at the bottom, it continues going straight and dimensions everything accurately. One of the funny things about machining is that you accidentally create fidget toys like all the time. This is like really hard to stop doing. Next, I create the larger counter bore on the end of the part, as you can see in the drawing. And this counter bore, as I said, acts as a thrust surface for the shaper forces, but it also acts as radial thrust for the part, just in case any more support is needed radially. I don't expect a lot of radial forces from the shaper cutting action, but just in case, this is going to surround the end of the main spindle and support it that way as well. All right, that's it for the lathe work. We're ready to part this thing off. And Yahtzee. Moment of truth. Let's see if I got a good fit. Because of that setup, I wasn't able to test it before taking it down off the lathe, so I just had to go by the numbers and see if I know what I'm doing. And the good news is, it seems like I do. At least a little bit. That is an amazing fit on there, and that thrust surface sits firmly against the frame just like I hoped it would. That's looking really good. Now, let's go over to the mill and do some set screw drilling. There's 2 set screws opposite each other on this collar, and these act as the spindle locks. Again, a spindle lock may not be necessary because of the direction of the cutting forces in this setup, but seems like a good idea. I was able to drill those 2 opposite holes straight through, but I can't tap them straight through. My tap isn't long enough, so I need a way to index this. I don't have a collet this size, so I wasn't able to index with a collet block. So instead I'll bring in the rose index, set that on the part, use that to index 180 degrees so that I can get the tap lined up for the other hole. These holes are going to hold brass-tipped set screws so they can clamp down hard on the spindle that's riding inside this collar without marring it up. That's the main bushing done. Let's do a little test fit of all of the accoutrements from the Vertex rotary table. Make sure it all fits. So the index plate will go on there. The hole's all lined up. It's a good thing. Then the sector arms go on there. And then there's this kind of slightly goofy spring clip thing that the Vertex uses to hold the sector arms and put some preload on them. And then you can clamp down with this little screw to hold the angle of the arms relative to each other. And that's all looking good. And then the axle will go through that and the crank arm attaches to the end of the axle. This is an awesome start. So far everything is going to plan, touch wood, but we have a lot more to do yet, and I am out of time for this week. So thank you so much for watching. Thanks to my patrons for making this all happen, and I will see you next time.